Welcome back to GLS4OM, continuing our work in Unit 8, Applications of Integrals. We had looked at the washer method, volume of revolution for the washer method, and we said if we have a curve y equals f at x and we're going to rotate it about the x-axis, then we would use the washer method. Today we're going to take that curve y equals f at x and we're going to rotate it about the y-axis, and we're going to see we're going to have to use a different method called the shell method. But what we're going to do is we're going to start with our humor for the day. So I'll let you take a look at those two comics. I'm going to get my pen set up while you're doing that. All right, so some interesting trivia here. So Dr. Seuss, we say Seuss, rhymes sort of with Mother Goose, and Seuss was actually Theodore Geisel's middle name, and it was actually pronounced Zeus. And he was okay with, if you called him, if you spoke to him, you would say Theodore Zeus Geisel. But he was okay with being called Dr. Seuss. So here we have Dr. Seuss. What would happen if you were Dr. Zeus? And of course, we have the Greek god Zeus throwing the lightning bolts down, but looking very much reminiscent of a Dr. Seuss character. Interesting play on events there. And this one is interesting. I don't like green eggs and lamb. I don't like them at all, madame. Not with Hades, not with the ladies, not as a treat on the island of Crete. I will not eat them, Persephone. I will not eat them. Let me be. A nice little rewrite of a Dr. Seuss poem. All right, moving forward. We're going to look at today's work. So I said volumes of revolution using the shell method. So we're going to take a curve that's written in terms of x and we're going to rotate it about the y-axis. So we're going to have a mismatch. The curve in terms of x but rotating about the y-axis. The washer method can't be used. If we're going to rotate this way, I would need this radius right here. And in order to get that radius, I would need to know what x equals g at y was. So if we're going to use the washer method, got to find the radius, and there has to be a match in the washer method. Y-axis, the function has to be in terms of y. I'm going to show you the shell method. If it's possible, I will show you an example. We'll do it two ways. If it's possible, you could rewrite the curve. So instead of being a function of x, it's a function of y, and then you try to use the washer method. The bounds of integration would also have to be switched, right? So instead of working on the x-axis bounds, we have to work on the y-axis bounds. Now, for some functions, it would be very difficult to isolate I said for y, but I really think I mean for x, right? Because we want to write x as a function of y. And so if we had x to the 7th plus y to the 5th, no, not y, plus x to the 5th minus 10 was y. We'd now have to isolate this for x, and you can see that would be very problematic. So it'd be worth it for you to invest in the shell method. So what's the shell method say? So this is going to get rotated about like this, and it's going to create a shell. And that one's going to get rotated around, and it will create sort of a bigger shell. So think of these shells as hollow. You see how in this picture, this diagram is better. We're going to pick like a delta x. That would be our width would be delta x. And then we're creating hollow shells, except for the very first one down there would not be hollow. But every other shell would be hollow. And then we're going to approximate the volume of this piece. We're going to find this sort of surface right there. That surface there. And then lay that flat. What we're going to get is a rectangular prism. And the thickness of that rectangular prism is going to be delta x. And then in order to find this, and remembering that that goes all the way around, I'm just going to come to the next slide just to show you that better. If we come all the way around like this, that dimension is going to be 2 pi r, the circumference. And the height would be this. So if we flatten it out, we're going to get a piece of paper. And if we were in class, I'd be showing you a piece of paper right now, flattened out, 2 pi r by h. And then each of these pieces of paper has a very tiny thickness, and that thickness is going to be delta x. then eventually we'd want to send delta x to 0, and we'd just be looking at that piece there. So that's where we're getting 2 pi r. That's where the h is coming from, and then delta x. And now we're going to dig a little deeper to figure out what are we going to replace the r with? What will we replace the x with? We know that delta x eventually is going to become dx. So moving forward. So I've shown you two shells here. A smaller shell and then a larger shell here. So I hope we can see that the height here and the height over there is going to be replaced by the function value at that x coordinate. So if this is the ith shell, then its height is f at xi. And then this distance right here, which would be the radius, that radius is just the x coordinate. So we're going to replace the x coordinate or the radius with the x coordinate of that particular shell. Because the x coordinate of that particular shell, so if it's the xi shell, whatever that x coordinate is, that's going to be the radius. And then the height is going to be f at xi. So there's the 2 pi, there's the r, there's the h, there's the delta x. The limit as n goes to infinity of the sum of all of these shells, then the shells become infinitely thin, so eventually, this little width here, that's approaching 0. So then we would definitely be tracing exactly out the curve. We're going to lose the jaggedness where we were having thickness here. The thickness is going to be disappearing. And we know all of this gets replaced by an integral, so it becomes the integral from a to b. 2 pi can come out in front because there are constants with respect to the variable of integration, which is x. And I now have this formula, 2 pi, the integral from a to b of x times f at x dx. And that is the formula for the volume of revolution using a shell method based on the formula 2 pi r h, and then times by the thickness of the rectangular prism, which was delta x. The previous day we were doing the volume of a cylinder, and the volume of a cylinder, this one is, I'm going to put RP for rectangular prism. We were approximating it using the volume of a rectangular prism. The previous day it was the volume of a cylinder, so we were doing pi r squared h. And then the h, the height, was our delta x, and the radius was our f at x. And then that would become squared. So that was the formula from the previous day. This is the formula today. And remember, we're using this when we are rotating a function of x around the y-axis. All right, so there's the formula. And again, a function in x is rotated around the y-axis. Cannot use the washer method, have to use the shell method. All right, the first example, you're going to find the volume of the solid created by rotating the region bounded by the x-axis in this curve from 0 to 1. And again, it's about the y-axis. That's how you know there's a mismatch. Function in x about the opposite axis. This is a shell method example. And it's our first time to ponder pause. All right, resuming to take this one up. So the formula for today, helping you remember this, it's 2 pi r h and then delta x, because it was the volume of a rectangular prism. So 2 pi r was one dimension, f at x was the other dimension, that was our h, and then the thickness, delta x, becomes dx. All right, so plugging into here, x stays x, so we have 2 pi x. Our f at x is root x, so I'll put root x there now. I'm going to bring the 2 pi out in front. Again, we've talked about it's a constant with respect to this integral. X times root x becomes x to the 3/2. And now we're ready to take the antiderivative of this. The antiderivative of x to the 3/2 is x to the 5/2 divided by 5/2. Add 1 to 3/2 and get 5/2. Now I'm going to invert and multiply because I'm dividing by 5/2. So 2/5 times 2 pi becomes 4/5 pi. And now I'm going to evaluate x to the 5/2 from 0 to 1. I showed you the 0 I was writing in here, but if I was in university, I'm not so sure I would write that if I was pressed for time. 0 to any exponent is 0, 1 to any exponent is 1, and 1 minus 0 is going to be 1, so we're just going to have 4/5 pi times 1, which becomes 4/5 pi. So that's just going to be 4/5 pi. I did a bit of a sketch over here, just to show you what we're doing. We're taking this region, and then we're going to be rotating it this way. And the volume of that solid would be 4/5 pi. Now I'm going to show you an alternate way. Okay, what would happen, or maybe do you want to think about that? Because we know the formula would be the integral from a to b of pi r squared, and that's going to be g at y. I'm going to put g squared y and pretend that that's valid notation. G squared y dy. And then you rewrite this as a function. It is now a function of x, but rewrite it to be a function in terms of y. And then you should be able to use the washer method because you're matching a function in y around the y-axis. So see if you can redo this and get the same answer using this formula. This will be our second time to ponder pause. All right, resuming and taking this out. So there was a bit of a twist to this. I am using this bit for the formula, the integral from a to b of pi times g squared y dy. We have rewritten our formula, y equals root x to x equals y squared, so g at y is y squared. But now we've got to do some thinking about what an integral does. What does an integral do for us? So an integral is going to, if I'm not thinking volume, the rotational part yet, I'm just going to think in terms of an integral. It gives me the area between the curve and the y-axis. So it's going to give me this green bit here. So the volume I'm calculating right here would be for rotating this green bit around the y-axis. And that's not the bit I want. I want the volume created by rotating the purple bit around. So what I'm imagining I'm going to do is I'm going to take this bit. I'm going to rotate that bit around the y-axis. First of all, like that. And I'm going to see I'm going to get a very large cylinder, right? And that's rotating. Just think of that square going around. That square there rotating around is going to create this large cylinder. And the radius of this cylinder is going to be this bit here, which is 1. So I had to start by doing the total volume. The total volume would be given by pi. I'm not sure why I've got an extra 1 written there. Let's just ignore that. Pi times r squared. The radius is 1. Radius given by this direction here. The integral from 0 to 1 based on this one. That radius I can see was the 1. So pi times 1 squared. That gives me pi as the volume of that whole thing traced out by that flat whole square there. And now I'm ready to take away the volume that would be created by the green region, so to speak. So the volume created by the green region now would be the integral from 0 to 1 of pi times y squared all squared. Y squared all squared is y to the 4th. So it's pi times y to the 4th dy. Now I am ready. I've got it set up. So I hope you understood the discussion I was having with you here. It's not just a simple matter of taking this integral, because that integral calculates the green area, and you want to rotate the purple area around, not the green area. So we started by just figuring out what would the whole volume, green and purple together. If you spun that around, you're just going to get one huge cylinder. I don't know if I called it a rectangle before. If I did, I meant cylinder. One whole cylinder, and the volume of that cylinder would be pi times 1 squared, which is pi. And then I'm going to take away the volume created by the green region. And the volume created by that green region, I'm going to change my pen to green, would be this bit right here. And now let's see if we get the same answer. So integrating y to the 4th, we get y to the 5th over 5. Just going to disable something. Got this flux thing coming on, and it makes the screen too hard to read. So I'm now going to get y to the 5th over 5, and again, the 0 is going to contribute nothing. 1 to any power is going to be 1, so I'm going to get pi times 1/5, which is pi over 5. And pi minus pi over 5 is 4/5 pi. So I do get the same answer, but I did not have to do any extra thinking about subtracting or whatever. The shell method gives me exactly the region I want. The washer method would not. This is not giving me the region I want, so I had to do a subtraction. So that's just a caution if you were going to use the washer method. All right, let's look at another example. Find the volume of the solid created by rotating the about the y-axis, the region that's bounded by these two curves. So you've got a region bounded by those two curves, and you're going to rotate it about the y-axis. Now let's see if there's a mismatch. These are functions in x, and this is the y-axis. That's how you know it's a shell method. And again, another time to ponder pause. Okay, resuming and taking this one up. So we found the formula for today. We know it's the shell method because there's a mismatch. We're rotating about the y-axis, and these are functions in terms of x. And we found that we should be using the formula 2 pi rh delta x because we were finding the volume of a rectangular prism. The thickness of the prism was delta x, and the length and width of our piece of paper, there was one there, 2 pi r, the other was h. So we know where that formula came from to help us remember it. So we're going to be plugging into 2 pi x f at x dx. Now I have to be thinking about what is this f at x a little bit. What's going on here? So let me get a pen and see if different color here, if I can walk you through this. Maybe I'm going to change this to red. All right, so what I'm doing now is when I'm going to spin this region around, I'm going to have to get the height of the shell right. What's the height of the shell? The radius we've established is always going to be given by the x-coordinate, so it's the height I'm worried about. So what is this little bit? How am I going to calculate what those bits are? And again, those little lines that I'm marking there are demarking the region. This is the region that will be spinning around. So I kind of brought it down here just to show you. There is one particular shell right there. There's the height of the shell. How do I find the height of the shell? Well, it should be the difference between the two y-coordinates. The y-coordinate for the curve y equals x, and the y-coordinate for the curve y equals x squared. So if I just do an x minus x squared, I should get the height of my shell. That will work all the way along. So if I want to find the height here, I need to take this coordinate here and subtract that coordinate down there. Same will work here. Want the height of this shell? And this shell is going to look something like that. If I want the height of that shell, then what I'm going to need to do is subtract that coordinate and that coordinate. So all the way up the curve, I hope I've convinced you that if you want to find the height of the shell, you should just be doing x minus x squared. And so now what I'm going to plug in for this f at x now would be x minus x squared. And this is no different from the work we were doing before. And you're trying to find the area between two curves. You did the upper curve minus the lower curve. That still applies here as well. So we've got our x times, that's the height. That would give us the area of that region, and that's what we want to rotate around anyways. And now expanding, I get x squared minus x cubed. And then taking the antiderivative, I'm going to, I don't even remember if I mentioned this, but I did bring 2 pi out because it's a constant with regard to this integral. I now have 2 pi times the antiderivative of x squared is x cubed over 3. The antiderivative of x cubed is x to the 4th over 4. And again, if I was in university, I'm not even going to bother to plug the 0 in. It's not going to contribute anything to the definite integral. So I'm going to be 1/3 minus 1/4. That's 4/12 minus 3/12, which becomes 1/12. So I now have 2 pi times 1/12, and that becomes pi over 6. So the volume created by this region and spinning this region around right here, that's going to be a pi over 6, according to the shell method. Now I want you to see if it is possible to redo this using the washer method. But in the washer method, we're going to be doing g squared y dy. And we're going to be doing a pi because in the washer method, we're not finding the volume of rectangular prisms, we're finding the volume of cylinders. See if it's possible to do this one. And I think this will be our last time to ponder pause. All right, let's resume and take this one up, doing it the alternate way. And let's see what happens. So, starting with this one, y equals x squared. I now want to rewrite that as a function in y. So I'm now going to isolate for x. Now technically I should have been getting x equals plus or minus the square root of y. But I'm only interested in this branch here, and that's the rightmost branch, and that would correspond to the square root of y. So x is the square root of y, and that's going to be the rightmost part of this. So I'm going to call that y right. Y right is g at y, which is the square root of y. And of course the other curve was y equals x, so if we isolate and we want to write it as a function of y, we're going to get x equals y. And I will rewrite that as h at y is equal to y. then I'm going to note that that is y left. And so now we're going to be tracing out washers right here. So I'm just going to show you. These are going to trace out washers now when we rotate this about the y-axis. And then I'm going to have two radiuses, right? I'm going to have, let me do this one in blue, from there to there. That would be from there all the way over to there. And let's do this in orange. Then we'd have the shorter one that's just going to go from there to there. And that would be this one from there to there. So the orange one would be represented by h at y. And the larger one, that larger radius from there to there, would be represented by g at y. So using the washer method, I want to find the area of that circle. The area of the circle created by the blue radius would be g at y squared times pi. And then the area created by, let's call it that orange radius, let's call it the area of an orange circle. So we really have got an orange circle. Let's try and sketch that in. Then we've got this blue one that's larger like that. And then what we're going to do is cut this one out of that. So I should have pi times the blue radius squared minus pi times the orange radius squared, which is in effect what's been written right there. Pi times, there's the square of the blue radius, and this one is the square of the orange radius. Then I'm ready to plug my formulas in now that I understand what this integral is telling me. So I got pi times g at y is the square root of y, minus h at y is simply just y. So when I square it, I'm going to get y squared. When I take the square root of y and I square it, I'm going to get y. So I'm now going to have pi times y minus y squared dy. I could have brought pi out at any point in time because pi is independent of the variable of integration, so it's a constant as far as this is concerned. The antiderivative of y is y squared over 2. The antiderivative of y squared is y cubed over 3. And bounds of integration from 0 to 1. And again, the 0 is not contributing anything, so I'm just going to go straight to 1/2 minus 1/3. Pi 1/2 minus 1/3, that's 3 over 6 minus 2 over 6, which is 1 over 6. And pi times 1 over 6 is pi over 6. So notice, let's jump back here. I got the same area showing you two ways. You can do it as the shell method or you can do it as the washer method. This one was a bit different. I didn't have to worry like I did in this one over here. It was going to give me the purple area. I wanted the purple area, but the integral I was setting up was going to give me the green area. We don't have to worry about that here because we've already addressed that by finding this region here. This subtraction gives us the correct region, so there was no extra worrying in this particular question. Let me see if I can get this to work over here. This is just showing you. All right, this is just showing you. I need to go a little bit. Whoops. Just want to show you how the shell method would work. So we're going to just start rotating it around, and you see how it's sort of filling in. I don't really need to go that far. Let's move it a little bit. And then if I grab that and just move it around, so you can see how it's creating shells, and you can see how that one's working. Hopefully that gives you a bit of a perspective on what we're talking about. I mean, I get that it's hard to see this when I'm just drawing something on a two-dimensional surface, and then I'm trying to impart 3D knowledge. So hopefully this made sense. If it doesn't, feel free to contact me. And again, I just want to summarize with, let me get maybe the blue pencil out. So W for washer method. When do you do washer method? So a function in X rotated about the X-axis, or a function in Y rotated about the y-axis. When do you use the shell method? You have a function in X that's being rotated about the y-axis, or we have a, I'm going to change that to a g, so g at y, or we have a function in y being rotated about the x-axis. So the washer method is used when there's a match between the variable the function's being written in, a function in terms of x about the x-axis, or a function in terms of y about the y-axis. Those are washer methods. If there is a mismatch, we have a function in terms of x about the y-axis, or a function written in terms of y about the x-axis. The mismatch will require the shell method. And I did note it's possible to, rewrite this as a function in x and use the opposite method, but that could require extra consideration in terms of the example where I showed you there was a subtraction. All right, so that kind of ties it together, the volumes of revolution using both washer and shell method. If you've made it to the end, once again, thank you. Don't forget to like and subscribe, and as always, take care and stay safe.